Hello, everyone. Welcome to this event of the 40 Under 40 lecture series on combustion. I'm actually glad to see you this Friday afternoon in Europe, morning in the US. I'm very pleased to introduce Dr. Samah Mohamed. She received a PhD in chemical engineering from King Abdullah University of Science and Technology, KAUST in Saudi Arabia, where she specialized in low temperature combustion chemistry. Her research focuses on developing chemical kinetic models, both for conventional and alternative fuels, and also she conducts quantum chemistry calculation. She is currently a research scientist within the fuel and combustion science group at the NREL, so the National Renewable Energy Laboratory. And there, her work focuses on net zero carbon fuels through the fuel design and kinetic modeling, and there is a particular emphasis on sustainable aviation fuels. So thanks again for having accepted our invitation. I give you the floor for your presentation. Thanks.
All right. Thank you, Alessandro, for this intro, and thank you and thanks for Salvador and Professor Ward for organizing these 40 Under 40 e-lecture series on combustion. It's really an honor to participate on these webinars. So today I'm going to share my work on the low temperature oxidation and combustion chemistry of alternative fuels, a work that I've been doing in the last 9 years or so. So before I start, I want to start by acknowledging my collaborators and sponsors and colleagues. Half of the work that I'm going to present today is done at KAUST, and I am sharing the screen. I cannot.
Yeah,
do you see my screen? Okay.
Yes.
Okay. Just yeah.
Perfect.
Okay, so so part of the work was done at KAUST. For that was sponsored by KAUST and Saudi Aramco. The work that I'm going to present today, part of it was also in collaborations with Professor William Green and Shamal at MIT. Special thanks to my advisor, Professor Mani Sarathi, and my mentors, Mariam Al-Rashidi, Zandong Wang, and Alexander Davis. The other part of the work I'm going to share with you today was done here at NREL, sponsored by ExxonMobil and the Vehicle Technology Office at the U.S. Department of Energy. That work was in collaborations with the group at the Colorado State University and the Lawrence Livermore and the Oregon National Labs as well. Special thanks to my colleagues, Nemal Nasser, and my PI and managers here at the group and mentors, Robert McCormick and Gina Ferroni. So let me just start by giving a glance about the group here at NREL. At NREL, we are the Fuel and Combustion Science group. We're mainly an experimental team doing a lot of fuel analytical chemistry, fuel property measurements, also auto-ignitions experiments. We have a wide range of hydrocarbon analysis experiments, 2D GCs, and also flow and thermal properties. We're also having a laminar flow reactors and constant volume chambers. We're also working in developing kinetic models, formulate surrogates, and reduce these kinetic models as well. The group is also it works closely with the standard, with the ASTM standard development. We're working on like fuel specification limits and providing such data, especially in diesel and ethanol. Like we had an experience in diesel and ethanol, and now we're working on aviation fuels as well. So in general, if you look at the group, we're working on like fuel design or trying to bringing new fuels to the market, right? And this brings me to the beginning of my talk, which is like most of the research that we're doing now in combustion is basically either we're looking for cleaner new fuels or we're looking for more advanced and more efficient engines. And I believe in both cases, we need to understand the hydrodynamic inside the engines. We need to understand the combustion processes inside the engines. But engine experiments are very complex. They are very expensive. They have a very varying parameters, like pistons are moving up and down. We have changing and fluctuations in temperature and pressures and mixture fractions. So it's really hard to do that. But one way to do it is actually to break down these engines into small phenomena and study each of these phenomena separately. So for example, if you want to study auto ignition, you can run RCM and shock tube experiments, right? If you want to do speciations and study the pollutants, you can run flameless experiments like jet state reactors and block flow reactors. These what we call fundamental experiments. It's mainly ideal homogeneous experiments, and they can be modeled experimentally. These experiments usually come hand in hand with chemical kinetic models. Chemical kinetic models are developed using these fundamental experiments, and at the same time, these kinetic models are used to understand some of the observations or some of the phenomena that we see in these experiments. So they are complementing with each other. Once you have a well-validated chemical kinetic model, then you can reduce it and use it in a CFD modeling of engine, and this is another way to study your engine. So you can see here, chemical kinetic model is in between. It's really crucial in the combustion research. But now another more complex problem is that the fuel that we're trying to study are even way more complex, right? There is a lot of hydrocarbon classes within each of these classes of each of these fuels. There are hundreds of species, if not thousands, if we're talking about conventional fuels. So it's really very complex, and we cannot develop a chemical kinetic models for these fuels. What we do is we develop a surrogate fuel or surrogate to represent the real fuel, which is basically 1 to 2 components that can represent the chemical and physical properties of the real fuel. Once you formulate your surrogate, then you can develop a chemical kinetic models for these components and then further reduce it if you want to use it in a CFD model. And today my talk is going to be focused, of course, in the chemical kinetic model part here. So I'll start by giving a little bit more details and some basics and fundamentals about the chemical kinetic model. So bear with me a little bit if you already know these informations, but I just wanted to make sure that we're all on the same page when I start to present the work that I'm gonna share with you today. So what are the chemical kinetic models? Basically, they are 3 files that we need to use to describe the combustion process. Combustion process is the reaction of fuel and oxidizer to give CO2, water, and heat. But this is the global reaction. In chemical kinetic models, we need a mechanism file to describe the elementary reactions in between. So we have a mechanism file that have all the elements, the species, and also the reactions, and thousands of reactions. To describe the competition between these reactions, we use the Arrhenius constant, which is the 3 numbers here, or you can look here at the Arrhenius parameters in the temperature-dependent Arrhenius equation. We have A, the free exponential factor, and the temperature exponent, and EA is the activation energy. These numbers are usually can be found experimentally, or you can do calculations, or also by analogy, in which if you don't have any rate constants calculated or measured, then you can use similar rate constants from another reactions that proceed with the same transition state and type of reaction. Another file here is the thermodynamics file. Thermodynamic files provides your specific heat, enthalpy, and entropy. And these are used to calculate, of course, heat release, heat of combustion, but most importantly, Gibbs free energy, which is really important to calculate the reverse rate of reactions for those forward rates. The thermodynamic files usually contains 14 NASA polynomial constants, so it's in the NASA polynomial format. We have 7 for the high temperatures, 7 for the low temperatures, and then you can find your properties. The third file is the transport file, which is usually used if diffusion is a rate limiting step. We provide some kind of geometry constant, Lennard-Jones potential, well depth, and collision, so you can find other properties like viscosities and diffusion coefficients. Again, today my focus is going to be in the mechanism file. So how can I develop a mechanism file? As I just mentioned, I'm talking about thousands of reactions. One way is to use the automatic generation algorithms like RMG, for example, reaction mechanism generator, which is well known, developed by the group at MIT and Northwest University. Or alternatively, we can do the hierarchical approach, or we call it manual approach. So for this, you start by your fuel. And for that fuel, you include around 25 to 30 classes of reactions. So it's well-known classes of reaction. You follow them. Within each classes of reactions, you have maybe 10 to 20 reactions, maybe less. So this is for the fuel. For example, if I'm building a kinetic model for a heptane, then I need to include these class 2 reaction for heptane. But then heptane is going to decompose, right? We have some decomposition pathways. So we have intermediates form, and then we need to include the intermediate submechanism. And then until you reach C4 chemistry, which is we call C4 to C0, we call it the base chemistry. It's a model that's already developed in the literature, like GRI MEC and Aramco MEC. It should be very comprehensive, well-developed, well-accurate model, because it really affects the accuracy of your overall model at the end of the day. So this is how we develop a model. We include all of these reactions. And today I want to focus on the low temperature chemistry. Low temperature chemistry, I'm quite sure that most of you are aware of it, because we usually know it by this low temperature schemes. You've seen it 100 times for sure. But I'm just going to go through it a little bit again, because I'm going to refer to it a lot in my talk later. So what we mean by the low temperature oxidation chemistry, apparently you have a oxidation process. You start with a fuel and oxidizer. So what happens if the oxidizers attack the fuel? It forms a radical where it abstracts a hydrogen. This radical is very reactive, and at that time there is a lot of oxygens around, so the oxygen is going to add to the radical. We're going to form RO2 radical. Now you have a peroxy group that's very reactive and unstable molecule, so the peroxy group is going to undergo an intramolecular hydrogen isomerization and abstract the hydrogen from the back chain of the molecule, and forming a QOH radical. Now the radical is transferred to the back to the chain of the molecule. Again, unstable and very reactive. So we're going to add an O2 and then forming the O2 QOH. O2 QOH is very reactive. And what happened here, it undergoes another intramolecular hydrogen isomerizations, hydrogen abstraction or isomerization, and it forms a keto hydroperoxides and release an OH. And these hydroperoxide release another OH. So you start with one radical and you ended up with two radicals. And this is what we called a chain branching reaction. Chain branching are very reactive, very exothermic reaction, in a way that if you look at the reactivity with your reactor of temperature, now you can see that the reactivity increase as you go from top to bottom. Now the temperature increased in a way that you start to activate new pathways, which are the pathways in green. So for RO2, instead of it isomerized to form the QOH, now I'm going to form olefins and water. We're going to form both, but now olefins and water starts to play a role as well. For QOH, instead of adding O2 addition only, it can form olefins or cyclic ethers, or it can undergo a beta session. So these are competing reactions. If you look at these reactions, you start with one radical, you end up with one radical. We call these chain propagation reactions. You can see that chain propagation is competing with the chain branching reactions. And also the radicals forms are HO2 radicals compared to OH radicals that I used to form before, right? So if you look at the reactivity now, you can see that my reactivity starts to decrease because of these chain propagation reactions compete with the chain branching reaction. Until you reach a temperature maybe around 900 Kelvin, where these HO2s self-react with each other, forming H2O2, and then these H2O2 breaks to form two OH radicals, and now I restore my reactivity. OH starts to attack the fuel or other intermediates again, and you form a radical. This time the temperature is high enough in a way that the radical, instead of adding O2, it's going to isomerize or form olefins and another pathways. And if you look at the reactivity, we see that the reactivity restored for your reactor. So this phenomena here is what we call a negative temperature coefficient, where you see that the reactivity decrease as the temperature increase. It's well-known phenomenon in the low temperature chemistry of hydrocarbons, but here I'm just showing some examples from the literature, just random examples for heptane, isooctane, 1-butanol, and butyl ethers. And you can see their ignition delay time versus 1/T, which is a measure of reactivity. For heptane, we see an NTC. For isooctane, a mild NTC. And at some conditions, we cannot see NTC. For 1-butanol, there is no NTC, and so forth. These reactivity also can also be seen in terms of speciations, like in blood flow reactor or jet set reactor. So here we see that the heptane also does have an NTC, isooctane and butanol does not show any kind of NTC. But more interestingly, when you look at the dibutyl ether, they even show 2 NTCs or a double NTC behavior, as we're going to talk about later. So this brings us to the question of that I want to pose in this talk of how do the hydrocarbon structures would affect the low temperature chemistry and reactivity of our molecules? How just by changing the functional group, we will have different reactivities. And we want to dig deeper into the low temperature chemistry and start and understand how that happens. So today I'm going to cover with you 4 different functional group or 4 different hydrocarbons. We're going to look at isoalkanes. Isoalkanes are very important hydrocarbon class in different fuels. For gasolines, and also recently we start to look at that in the SAF fuels and aviation fuels, and we're going to look particularly to 2-methylhexane. For alcohols are well-known biofuels, but we're going to look at what are the governing chemistries on these alcohols. We look for esters. Esters and fatty acid methyl esters are the major components in biodiesels, and ethers are also a very well promising biodiesels blend stocks. So we're going to look for the low temperature chemistry or the governing chemistry or just the chemistry of these 4 different functional groups. All right, so we'll start with 2-methylhexane. 2-methylhexane, as I just mentioned, it was proposed as a gasoline surrogate in the phase of fuels. It represents around 7% of the surrogate. So the model was already developed before when I start working on that. But at that time, there were many rate constants that start to be calculated in the literature. And here in this slide, I just want to show you the importance of having accurate rate constants and how that would affect the measured properties or the calculated properties from your simulations. So this is the low temperature scheme that I showed you before. This is the ignition delay time versus 1/T for 2-methylhexane as developed by Sarathi et al. And then when I start updating the model, so I found the new rates for the fuel abstractions by OH. So I changed the rate constants in that model, and you can see there is a minor effect. The first O2 addition, again, there is a minor effect, as you can see by update number 2. When you go to the isomerization, update number 3, we can see there is a huge increase in the reactivity. And so forth. So going to update number 4, 5, 6, 7, and 8. And 8, you can see there is a noticeable increase in the reactivity of the molecule. Update number 8 is basically the conventional isomerization of O2 QOH to the keto hydroperoxides plus OH, which I just showed you as the most important chain branching reaction at the low temperature chemistry. Even went one further step for the keto hydroperoxide decomposition, which releases another OH. So it's really important, and you can see it had an effect on ignition delay times. So by this, as I just mentioned, I want to show you rate constants, accurate rate constants are really important, and also that the conventional isomerization turns out to have a very huge effect on our predicted properties. So another thing that I want to show you here, if you zoom in into one of these reactions, so here I just want to show one example of the O2 QOH. So we have a 2-methylhexane and a peroxy group and a hydroperoxide group. Conventionally, this peroxy group is going to abstract the hydrogen that's alpha to the OOH group because it's the weakest. And it's gonna abstract the hydrogen or isomerize. So the hydrogen will, the peroxy will take the hydrogens, and you have a radical here, undergoes a beta session, releasing an OH and forming these keto groups. This is the normal pathway. This is the most important chain branching pathways. But in some cases in 2-methylhexane, we realize that this pathway is chemically prohibited because there is no hydrogen available that's alpha to the OH group. So this pathway cannot happen. Alternatively, the peroxy group can abstract any other hydrogen that's available, for example, this one. And this is what we call alternative isomerizations. So we added alternative isomerization to the 2-methylhexane. We included all 6 member rings for all the O2 QOH radical. Here I'm just showing one example, and then we decompose those reactions. So when you undergo alternative isomerization, we call this the POOH2 or the dihydroperoxy alkyl radicals. Unfortunately, when we wanted to add this pathway to the model, there were no rate constants for this reaction. So we used analogies to RO2 to QOH. So analogy basically using the same rate constants for RO2 to QOH for this reaction, even though there is an extra hydroperoxy group, but we assume that the rate constants is going to be the same. Sometimes you can apply some corrections if you're abstracting from a weaker abstracting a weaker hydrogen or so forth. So after adding these reactions, we had around maybe 180 reactions added to the model, and we tested this in ignition delay time, and you can see that we increased the reactivity again. So what we can get from these two methylhexane study is that we can look at the low temperature chemistry and identify two pathways like the conventional isomerization, which is the one here, update number 8, and also the alternative isomerization we see here to the left as really two important reactions. The one to the right was already studied in the literature. There were a lot of rate constants, but there were some gaps. It's either the calculations were not as accurate as our current computational power, like we can do better, or there were some gaps for the calculated rate constant. So it's not site-specific rates for all the possibilities. To the left, the alternative isomerization, as I've just showed you in the previous slide, we used analogies because there is no rate constants. So we even don't have a solid conclusion about their importance. Are they really very competitive to the keto hydroperoxide? So that the question we wanted to have a solid answer for. So for that, we decided to do a systematic calculations for the QOH conventional and alternative isomerization pathways. For that, we used a theoretical method. We used the transitional state theory, fitted over the Eyring equations, and then the fitted over different temperature range to find the A, N, and EA that we use in our kinetic models. For that, we use Gaussian 0.9. We start by doing confirmation analysis, locating the minimum, and then optimizing and frequency calculations with a higher level of theories. We do energy calculations with 3 different methods and an average. And then we do some corrections with the Hendrix rotors and IRC calculations. The output from these calculations were used in ChemRate to do the fitting for the Eyring equations and get the rate constants. We applied these calculations to these systems. To the left corner here, I'm showing the system we considered for conventional isomerization. We looked from 5 to 8 member rings, all the possibilities, because isomerizations, it's basically closing a ring. So we looked for 5, 6, 7, and 8, and all possibilities of where your peroxy and hydroperoxide is. So we ended up with all of these species to do the calculations for. For the alternative pathways, we looked for all the butane isomers by changing where the peroxy and hydroperoxide is. So we ended up with all of these. And for each one of those, we looked for all the possible reactions. Conventional isomerizations, all possible alternative isomerizations. We also included concerted eliminations and edge exchange. We just wanted to make sure what other pathway can be important. All right, so to look at the results, I'm going to start by looking at the conventional isomerization results. Apparently, we're calculating rate constants, or here I'm showing rate constants versus 1/T. The first thing that I want to share with you here for 2 different species, and each of these lines are for 5, 6, 7, or 8 member rings. Apparently, we can see the 5 member rings are the slowest, as we know that the 5 member rings are so strained. But the thing that I want to share with you is that we always say 6 member rings is the fastest, right? This is the conventional kinetic model when we develop kinetic models. But I want to show also that 7 member rings turns out to be really important at some point, especially at low temperatures. So this makes us think when we consider 6 member rings, we may also want to consider 7 member rings because they are really important. Looking at the comparison with the literature, compared to the other 3 rate constants from the literature, at some points we can have a very good agreement. Sometimes you can see a discrepancies because of the entropy, because, for example, CHARM may use couple Hendrix rotors, we use 1D Hendrix rotors. Also, the different level of theories used for the energy calculation results in different discrepancies, especially at low temperatures. But the advantage from our calculation is that we considered all site-specific rate constants, so we are not going to do a mix and match or some kind of analogies. So we applied our rate constants into 2 kinetic models, 2-methylhexane and isooctane. You can see in 2-methylhexane to the left, the the dashed line are the original models. The red line, the solid lines are the one after using our rate constants. And we can see there are like barely any kind of effect. But looking at the isooctane, you can see that using our rate constant increased the reactivity. So that tells you that it might be important in certain cases, especially when there is a highly branched molecules like isooctane, because we consider the tertiary side that was not considered before in CHARMA. Okay, so this is in terms of conventional isomerizations. Looking at the alternative isomerizations, here I'm sharing the results for 4 different butane isomers. To understand these plot, we can look here at the scheme. The black lines is corresponding to the conventional isomerization. The blue lines are considered are corresponding to the alternative isomerizations. The red lines are conserved eliminations and also exchange in the gray one. And you can see the reactions here for one example. So we're not going to go through all of these lines, but what I want to share in general, if you look at the 2 plots to the left, you can see the black lines are really the fastest compared to the blue lines. That means conventional isomerizations are really more important. And when we start to look why, we figure out that because it proceeds via 6 or 7 member rings compared to 5, 6, 7 alternative isomerization. However, if you look at the right, you can see that the blue lines are faster than the black line. So that means alternative isomerization are more important than the ketohydroperoxides. And when we looked why, we figured out that these alternative isomerization proceed via 6, 7, or 6 member rings compared to 5 member rings conventional isomerization. So that means if you have a branched alkane, definitely include alternative isomerization. If you want to include the alternative isomerization for all the other pathways, but you don't want to include too many reactions, maybe you can consider alternative pathways where they are going to compete with the 5 member rings conventional isomerization because they're going to be important. In other cases, they're going to be less competitive with the conventional isomerization. So these are the results that we got from our work in the branched or isoalkanes. And next, I want to move to the alcohols or the isobutanol. As we just mentioned, alcohols, very promising biofuels. They're already extensively studied as a gasoline and diesel blends, and sometimes it's just stands alone in an SI engines. But the motivation of this work was exactly the plot that we can show, we can see here to the right. So this is ignition delay time versus 1/T. RCM data was run by Weber and Sung. The blue lines are the RCM data, and the gray lines are a kinetic model developed by Sarathi et al. The red lines are another kinetic model developed by Martian et al. You can see the 2 kinetic models does not agree with the experiment, which is okay, but even they don't agree with each other. Maybe Sarathi et al. Does have a better agreement at the low pressures, but again, the models, really, there is a discrepancy between the 2 models. Looking at the 2 models, Sarathi et al., which is the gray one, was developed by Sarathi using the hierarchical approach. The red one was developed by Martian et al. Using the reaction mechanism generator. So the question was like, why we do have 2 models that really behave differently? And we just wanted to apply some analysis to the 2 models and try to understand what's the sources of discrepancy. So the first thing we run is we just run a speciation like a mole fractions in a homogeneous conditions, mole fractions versus, over time, and also the temperature over time. So the blue lines here are the temperature to the right y-axis. The dashed line are Sarathi model, the solid line are Merchant or the RMG model. Both models showed 1-stage ignition, which is expected for the alcohols. As we've seen previously, it doesn't show an NTC. But in terms of the speciations, we can have actually 2 different slopes. So we can say we have 2 substages here, and each substage is governed by different chemistry. We've seen that HO2 governs the first substage, and then OH governs the second substage. Still, the model shows quite discrepancy here. We've also run a flux analysis for the 2 models to understand what chemistry we've seen here. Apparently, we have an alpha radical, which is alpha to the OH group, and we have a beta radical, and we have a gamma radical. Looking at the alpha chemistry, we have a radical, the low temperature chemistry, we add an oxygen, we're forming a peroxy group. The peroxy undergoes a low temperature chemistry. But in the alcohols, it turns out that this peroxy group forms an aldehydes and HO2. And like 100% of Mershon model goes to this aldehyde plus HO2, and there is no low temperature chemistry. In Sarathi et al. Model, he even thinks that this reaction is really quite fast in a way that is just going to go a formally direct pathway with like radical plus O2 directly forming aldehyde plus HO2. Remember the chain branching definition. You start with one radical, end up with one radical. So this is a chain propagation reaction that competes with the low temperature chemistry and definitely going to decrease the reactivity of your alcohols. In terms of the beta pathway, both models agreed very well in the chemistry. For the gamma, both models agreed that low temperature chemistry is really important, but the Mershon model actually showed another pathway, which is a water elimination pathways forming an alkoxy and a water. That was a new pathway that we couldn't find in Sarathi's model, but at that time it was like, okay, it's just a new pathway. But when we run a sensitivity analysis, we've seen that Sarathi et al. Model was quite sensitive to the pathway for the alpha radical, the chain propagation, while Mershon et al. Model was very sensitive to this water elimination pathway. So now to understand whether these pathways are the source of discrepancies, what we try to do is just make the two models look the same. Just having the two pathways look the same in both models and add the water elimination to Sarathi et al. Model. And this is what we get. This is the plot that I showed in the previous slide for the mole fraction with time. You can see now the mole fractions on top of each other. The temperatures also, they are looking very good. There is a very minor difference here, and most probably because Sarathi et al. Model does have more low temperature chemistry, and that's why it's a little bit more reactive. Even looking at the plot that I showed at the beginning as the motivation for this work, you can see here to the right, after we updated the model and simulated the RCM, we had models that agree very well with each other. And we even run the RCM experiments, and we had a good agreement with the kinetic model, with the experiments. So in general, what we need the takeaway from the alcohol chemistry is that the chain propagation pathway of alpha RO2 to aldehyde plus HO2 is the most important reaction. That's proved experimentally. Water elimination might have an effect, but the effect was a little bit less than the chain propagation, and we don't have enough evidence in the literature about this pathway. But RMG showed that this pathway is an important pathway, apparently. Okay, so this is in terms of alcohols, and now I'm going to move to the esters or the fatty acid methyl esters. So as we know that biodiesels are technically fatty acid methyl esters, but one of the challenges in the biodiesel is the availability of the feedstocks. And that's what motivated research to look for unconventional ways to produce these biodiesels, for example, looking for engineered organisms. Genomatica, the company, developed an organism that can produce a fatty acid methyl ester fuel. And these fatty acid methyl esters was like 90% fatty acid methyl ester, but they were around 9% of a beta hydroxy fatty acid methyl ester. So it's a fatty acid, but with an OH group. So looking at so we've been approached by ExxonMobil in collaboration with Genomatica to try to understand the properties of these and the effect of the OH group, how this is going to affect the performance of fatty acid methyl ester. Is it something good or bad? So we wanted to look at the effect of the OH group. So to do that, we decided to go with a surrogate because the fuel itself was, the chain was a little bit quite long to do a kinetic model for. And we also wanted to do a comparison study. And in the literature, there was already a methyl hexanoate kinetic model developed by Daima et al. So we decided to use the methyl hexanoate and the analogous methyl hydroxyhexanoate and then compare the chemistry. The methyl hexanoate is really good because the chain length is long enough that we consider all the possible isomerizations, and also it's short enough that we can have a detailed kinetic model for it. So the approach of this study is that we did an experiment for both methyl hexanoate and hydroxyhexanoate in a flow reactor and also in the AFIDA to measure some ignition delay times. And we run we developed a model for the methyl hydroxyhexanoate using RMG. And then we simulated RNG in Cantera. We applied some quantum chemistry whenever necessary, and then we compared these simulations and applied some analysis. So these are the results here. Everything in red is methyl hexanoate. Everything in blue is methyl hydroxyhexanoate. We have the flow reactor results to the left at both 1 and 10 bar, and also the FE here to the right at 3 different conditions. As I mentioned, methyl hexanoate model was already developed by DIMA. The only thing that we did is we had to update the base chemistry. So we can have similar base chemistry in both species. So we have a comparison between the species independent of the base chemistry. But in general, you can see that the two models reasonably agree with the experimental data, and we can do further analysis. So yeah, looking at the ignition delay time, also zooming in a little bit in the ignition delay time, you can see that the methyl hexanoate is actually less reactive than the methyl hydroxyhexanoate, right? So we run a flux analysis and sensitivity analysis at these conditions. The first one I'm showing here is the methyl hexanoate flux analysis. It's a normal chemistry. We have some, based on the bond dissociation energies, there are some radicals that bond dissociation energy and abstraction rate constants as well. It shows different fluxes, but all of these radicals are eventually going to undergo a normal low temperature chemistry, terminating via keto-hydroperoxides or another chain branching reactions. But looking to the right for the methyl hydroxyhexanoate, the first thing we notice is that we have 50% of the methyl hydroxyhexanoate forming this radical, which is alpha to the OH group. This is expected because the presence of the alpha OH group would make the bond dissociation energy very weak, right? So we form this radical, and if you look at this functional group here, it's just like an alcohol. We've just showed in the previous part that alcohols, when you have an alpha radical, it undergoes a chain propagation pathway, adding an O2, releasing an HO2, and then forming this ketone group. So this pathway is a chain propagation pathway competing with the low temperature chemistry. So we expect to see a decrease in the reactivity of the methyl hydroxyhexanoate. We even run sensitivity analysis, and even here I'm showing the sensitivity analysis for the flow reactor just to show that even the flow reactor shows the same. For the methyl hexanoate, we can see that the low temperature chemistry, maybe a little bit of beta sessions, are the governing chemistry. And for the methyl hydroxyhexanoate, we can see the highlighted reactions are basically the formation of the 3J radical and then the chain propagation pathway radical. They were among the most sensitive reaction, and they even showed a positive sensitivity, meaning that we are these are competing with the pathways that will help in converging the fuel, or for the fuel conversion. Another thing that if you look at the low temperature chemistry for these methyl hydroxyhexanoate, it ends up with forming a POH2 radical, which is an alternative isomerization product. And this is because for this OH to be in a secondary radical, it as a secondary radical, it makes the formation of keto hydroperoxides chemically prohibited again. So if you have this keto hydroperoxides here, O2QOH here, this peroxy is basically abstracting a hydrogen from the carbon that's alpha to the OH group. But because of the presence of the OH group, there is no available hydrogen. So the only possibility is to undergo an alternative isomerization and forming the POH2 radical. Again, alternative isomerization is competing with the conventional isomerization and decreasing the reactivity of the methyl hydroxyhexanoate. Even looking at the OH formations in the methyl hydroxyhexanoate, we can see most of the OH, or part of the OH, is formed from these pathways. So they are really controlling their chemistry. So yeah, that was in terms of the hydroxyhexanoate. And then moving forward to the ethers, we looked for the dibutyl ethers isomers. Again, ethers have been studied as a very promising biodiesel blend stocks. They can help in the atomizations and result in less soot. So what we want to look at is if we can form these ethers from a renewable resources. So one of the pathways is the Gorbet coupling, where you form a these alcohols from renewable ethanols, you form higher alcohols, and then you can undergo dehydrogenations to form these ethers. So these ethers from the Gurbet ethers, this is how they look like. They are a little bit, have a longer chain, long chains. They have some kind of symmetric and asymmetric, and also they have some kind of branches. So these ethers, if you look at the literature, we have an extensive study about diethyl ethers and maybe dinormal butyl ethers, but it's barely looked at the effect of the branch on the ethers on the literature. So again, we've been approached by ExxonMobil to start to look at these ethers from Gurbet ethanols and just understand the properties and also the effect of these different structures on their combustion characteristics. We followed the same approach of a study, but this time again, instead of looking at the Gurbet ethanol, the ethers from Gurbet ethanol, we decided to look for a surrogate again. We looked for dibutyl ether isomers just to have like asymmetric ethers, which make the kinetic studies a little bit easier. And they were very interesting because if you see, this is the normal dinormal butyl ether, and then this is the diisobutyl ether, and then moving the branch just one carbon to the left to form the disec butyl ether really affect their cetane numbers and reactivity, as you can see here. So they were very interesting isomers to look at and study, and then once we have an understanding of those ethers, we can expand it to the Gurbet ethers. So we looked again we looked at laminar flow reactor experimental study, and also we developed the models using RMG for the diisobutyl ether and disec butyl ether. Dinormal butyl ether was already in the literature, and we run a Chemkin simulations, and we did calculations whenever necessary. And of course, later we compared with the experiment. So here I'm showing the results for the dibutyl ethers, the three butyl ether isomers. To the left, I'm showing disec butyl ether, diisobutyl ether, and dinormal butyl ethers at both 1 and 10 bar for each. And in general, we can see we have a reasonable agreement with the experimental data. Zooming in a little bit to the reactant, just to start comparing the isomers. If you look at those reactant together, the first thing we can notice is the different reactivity. And here reactivity is defined by the temperature at which they are starting to get consumed or the temperature they will get fully consumed. So you can see disec butyl ether is a little bit less reactive than the isobutyl ether, less reactive than the normal butyl ether. And another thing to notice is the NTC behavior. Disec butyl ether doesn't show any NTC. We had an NTC behavior for diisobutyl ether, and interestingly, 2 NTC behaviors for the dinormal butyl ether. So start looking at the NTC behavior. There were a study in the literature by Tran et al. Where they did a probing for the dinormal butyl ether in a blood flow reactor. And based on the intermediates and speciations, they come up with a hypothesis of the reason for this noticed double NTC. So this chart here from the paper, I just wanted to simplify it. So I added the low temperature chemistry I showed earlier. So their hypothesis is that the first NTC is happening because the competition between the second O2 addition and the beta session of the QOH radical. And the second NTC behavior is basically happening because of the competition between the first O2 addition and a beta session of the radical. Or you can see this here in the scheme. So in order to test this hypothesis, what we did is we run a sensitivity analysis at the 2 NTC regions. So we run a sensitivity analysis of 500 Kelvin and 600 Kelvin. We're not going to go through all of the reactions, but I highlighted here 2 reactions. This one, which shows a negative sensitivity, is basically R2 reaction based on their nomenclature here. So R2 is the second O2 addition. And the R4 is the beta session of this QOH radical. So apparently at 500 Kelvin, when we see the first NTC behavior, we can define these R2 and R4 as 2 sensitive reactions. And in the opposite direction, that means they are really competing with each other. Looking at the second NTC, or the sensitivity at 600s, we identified the reactions of the O2 to the radical, which is the first O2 addition, or the radical beta session as 2 important reactions in opposite directions of the sensitivity. That means they are competing with each other and result in the second NTC that we see. So somehow that makes sense based on the kinetic models that we had for the dinormal butyl ether. And then in terms of the reactivity, to understand the reactivity of these three isomers, we run a normal flux and sensitivity analysis at both pressures, 1 and 10 bar. Again, I'm not going to go into the details, but I just highlighted the most important reactions. For disec-butyl ether at low pressure, it turns out to be very interesting, and it forms mainly secondary butanol and olefins. And we can see this by the sensitivity analysis as well. At high pressure, it undergoes a normal low temperature chemistry, forming ketohydroperoxides and mainly ketone intermediates. When we go for the diisobutyl ethers, this is the major radical. It undergoes a low temperature chemistry. Major components were the isobutanol. And then finally, for dinormal butyl ether, again, normal low temperature chemistry. This was the major component, forming mainly normal butanols. And this also supported by the sensitivity analysis. So what we can understand here is that all the three, maybe except for disec-butyl ether at 1 bar, they had a normal low temperature chemistry. So what's the difference? Why they have different reactivity? So we just looked at the intermediate pools that were produced from these parent butyl ether isomers, and we've identified them to be like normal butanol for dinormal butyl ether, isobutanol for diisobutyl ethers, and secondary butanol and 2-butanone for disec-butyl ethers. As you can see here, we're going decreasing reactivity from top to bottom. And if you look at the major intermediates, we can sort them with the same, going for a decreasing reactivity from top to bottom. We know secondary butanol is very less reactive, as we've seen because of the chain propagation pathways. Ketones are well known to be less reactive than the aldehydes. So now we know that these are less reactive. Looking at the two aldehydes here, the isobutanol is going to be less reactive than normal butanol because of the branch. Branch means alternative isomerization, means competing pathways to the conventional isomerizations. And then finally, the normal butanol can be relatively the most reactive compared to those. So this gives an indication that if you look at different ethers, looking at their key intermediates is correlated and can give an indication of their reactivity and can correlate well with their cetane numbers. So this is what we understand from these dibutyl ether isomers. We try to extend this to the Guerbet ethers, or the Guerbets formed from the, the ethers formed from the Guerbet ethanols. We had 3 ethers with a cetane number of 94, 93, and then 70. We don't have a kinetic model for, we didn't have experiment for, but what we did is just we sketched a low temperature chemistry similar to we did before based on our knowledge from the dibutyl ether isomers. And we identified those to be as a key intermediates. Those are asymmetrical ethers. That's why we have 2 major intermediates. This was with symmetric ether. That's why we just have 1 key intermediate. Looking at these 2 key intermediates here, we see that the branch is in the same position. So almost the same, suppressing reactivity effect. And then the difference is in chain lengths, which is balanced by the other combining aldehydes. That's why they are having a similar cetane number, or maybe very close, if you will. However, if you look at the third one, you will form this aldehyde having the secondary, the branch at the same position, but most of the species were this key intermediate. There is nothing else to balance the reactivity or the low reactivity that's happening because of this branch. And that's why we're having a relatively low cetane number compared to the other 2. So this is just one of the outputs we get from these studies. And we did a lot of property measurements to understand these ethers. But also while doing this study, of course, we run a lot of sensitivity analysis, trying to understand the chemistry. And all of these reactions that's in the blue box is basically a low temperature chemistry. And the ones in the red one are particularly the RO2 isomerization to QOH. It turns out to be very important. And when I was developing the model using RMG and I update some rate constants manually, I just figured out that there is no site-specific rate constants for ethers. We're using rate constants from alkanes, correct the activation energy, maybe by 3 kcals whenever I want to apply it for an alpha side. So this can introduce some kind of inaccuracies. So we decided to do a theoretical study to calculate the rate constants for the RO2 to QOH. We considered all possibilities similar to what we did before, 5, 6, 7, and 8 members. all the possibilities for where the peroxy is, like primary, secondary, tertiary, all the possibilities for where the radical is, primary, secondary, tertiary. And for ethers, it was a bit more complicated because the secondary, normal secondary, is different from a secondary that's alpha to the ether functional group. It's quite different. So we had to add this in the calculations as well. And also abstractions happening in the same side of the ethers are different from abstractions happening from the two sides of the ethers, because the ether functional group will be within the transition state or out of the transition state. So it was a little bit complicated. We ended up with having 120 reactions to calculate for this class of reaction. We used G4 level of theory using the same methodology that I've shared before. So let me quickly share the results here. We have a rate constants versus 1/T, just showing in comparison with the literature. The literature, we have a lot of rate constants for the diethyl ethers. So just showing comparisons. And in general, we have somehow a good agreement with the experiment, with the studies in the literature. Of course, there would be some discrepancies because of the different level of theories that's used. In terms of comparison with the alkanes, and I'm comparing with alkane because, as I just mentioned, I was using alkane chemistry for this pathway when I developed the model. So I want to see how much, like the amount of error that I have because of using these alkanes. In some cases, using alkane chemistry was totally fine and okay, and the rate constants were very close to each other. But in some times, you can see that alkane chemistry would overestimate the rate constants. In others, it underestimates the rate constants. So it's really important to use site-specific rate constants for the ethers. We even tried to use those ethers in our diisobutyl ether. So we updated the model using the new rate constants. The blue ones were the original model using the alkane rate constants, and the red one is using the rate constants we've calculated in this study. You can see it increased the reactivity a little bit for it decreased the reactivity a little bit for the diisobutyl ethers. In terms of acetone, it does have maybe a little bit better agreement with the experimental data when we update the rate constants, which is basically looking at the acetone, we can see that it forms from two different radicals. And by updating this rate constants, we just shifted the formation of acetone from the highly produced alpha radical to the less produced beta radical. And that's why we're having a less acetones and a better agreement with the experimental data. So this is what I want to share in terms of ethers. And just to summarize, going back to my outline slide, we looked at 4 different functional groups. In 2-methylhexane, we've learned how alternative isomerizations are really important for branch molecules. For alcohols, we've seen how the chain propagation pathway is really important and governing chemistry. For the esters, we look at the beta-hydroxy esters. And it was really interesting because it does have a very high conversion because the weak hydroxyl, but then at the end of the day, terminate with very less reactive pathways. And in terms of ethers, we've seen how just changing the branch 1 carbon to the right or left would have a huge effect on the reactivity and how we can correlate the reactivity to the key intermediates. So this were our attempt into different gasolines and biodiesel surrogates in components. And before I start taking your question, I just want to have 1 minute showing what we're currently do in terms of sustainable aviation fuels. Right now, we are working on, we know that aviation fuels contribute to 12% maybe of the transportation section in the US. And and we are having a goal of net zero emission by 2050. And this plot shows you the different technologies we have to adopt if we want to reach this goal. Most part of it is related to the aircraft and infrastructures, but the majority is basically SAF fuels. So they are really critical to reach this goal of net zero emission. So this made a government-wide initiative to produce around 35 billion gallons per year by 2050, so we can reach that goal. And right now, maybe we have 9 pathways for approved SAF fuels, but HEFA SPK is one of the most promising one. Right now, it can be blended by up to 50%, reduce greenhouse gas emission by 80%. So we decided to look into the HEFA, but HEFA is already used, but what we try to do is try to use HEFA as 100% drop-in fuel. We want to make HEFA suitable to be used without blending with conventional fuels. We know there are some shortcomings in the HEFA. For example, it doesn't have aromatics. So we want to understand how HEFA with aromatics or cycloalkane will behave in an aircraft combustor. So we want to do a CFD simulations. So our work is basically trying to develop a surrogate, reduce kinetic models, add aromatics, and then run some kind of computational modeling. I guess I'm going to stop here and start taking your question. Thank you so much for your attention. I really appreciate it.
Thank you. Thank you very much for this very, very, very nice talk. I really enjoyed it. Thank you. So there is time for questions, of course. Let's see if there is anyone who has a question.
Can I ask one question? Do you hear me?
Yuki, yes, thank you.
Thank you for the nice lecture. I think the very difficult thing in the low temperature chemistry modeling is that there are a lot of different branching ratio. So to determine the branching ratio in, for example, from R or from QOH or something. So there are so many different branching ratios. So I'd like to know what's your standard strategy to define these different branching ratio.
Yeah, that's a good question, actually. And we've looking at that, especially in the last study that I've just showed with you, like the ethers. I guess one of the most important thing in branching ratio is to make sure that you have a rate constants calculated using the same level of theory. So if you want to compare two competing pathways, but you're using completely different level of theories, that's I think is not a valid comparison to do the branching ratios, because basically branching ratio is the rate constants for one pathway over the rest, right? So this problems happens when you have a big class of reactions with 10 reactions, for example, and then some of them were calculated because you're using diethyl ether chemistry, but the others are using rates from analogy. So in that case, I believe branching ratio is not a valid comparison. And in the previous study, we showed we calculated the branching ratios over the temperature, and it shows that even like the solid lines are the one that we've calculated, the dashed lines are the one that we're using alkane chemistry. They even showed quite a difference, like factors of 9 and 35. So it's really important to have a rate constants calculated with the same level of theory, and then you can calculate your branching ratios and you can understand which pathways are the most important. If you have QOH to cyclic ethers or to olefins or to the beta sessions, if you have a rate constants calculated for these three pathways with the same level of theory, then you can have a right branching ratios of the competition between this. Right now, we're just using, I know in some cases like mixed rate constants, but this is what we've got right now until we have a fully more accurate developed rate constants for these low temperature chemistry. But that's a good point. Yeah, thank you for the question.
Okay, thank you. I have one more. So you consider alternative pathway in the very beginning of the presentation.
Yes.
And I think this is very difficult problem. Like, so sometimes in the model, you don't know, you may not include one functional group or like the pathways. So when do you realize you have to include like new pathways? You have to consider new pathways to adjust the predictions. Like what makes you
yeah, that's a good question as well. We've been like for that 2-methylhexane, we added alternative isomerizations, but we only included 6 member rings. So for example, the peroxy here can undergo 6, 7, or 8 member rings, but we only consider 6 member rings because we want to limit the number of reactions added. And we had around 180 reactions added just by 6 member rings. And because we just wanted to test the effect of alternative isomerization. What I did not share with you is that we even went further and we added a third O2 addition, and we added another subchemistry here, which was around 300 reactions or more, and just not for all the POHs, for just a couple of them, because we wanted to test some experimental observations where we had an O4 and O5 species. And you mentioned a very good thing that adding those reactions will have a better agreement with experimental data. And correct, we've showed that if you add these 500 reactions, you can have a better agreement with the experimental data, the black line here, without tuning the model. But the question at that time was like, is it feasible to add 400 reactions? And it's not. It's not feasible. Using these experiments, it was like to stress that alternative isomerization are important because we have some pathways that detected experimentally, so they are proven to be there and it's proven to happen. But I'm not saying we have to add third O2 addition. It's going to make the models quite big. It's going to make the models infeasible to run in the mathematical solvers. And at the end of the day, we know that these are predictions. We know that there are some errors associated with it. So we have some trials just to prove the point. But if you look at my 2-methylhexane model now, I don't. The published model, one of them does not have the third O2 addition because I know the users don't want 500 reactions for like extra 500 reactions that can might make their calculations very expensive. So this is a very good question. I was like, when should we stop? But we can go, actually, we can add as much reactions as you want. I guess we are right now governed by the computational powers available.
Okay, thank you, very interesting.
Thank you.
Hello, I managed to unmute myself eventually. Can you hear me? I hope.
Yes.
Yes.
Okay. So the question I would like to ask is, when you have shown that the biodiesel is composed of these beta hydroxy esters, you have shown that they might have also a double bond on the chain. And you have compared with hexanoate, and you have shown the difference in the behavior between the beta hydroxy and methyl hexanoate. Do you think that if you do the same and you compare with the hexanoate, so with the double bond, would this double bond have an impact or maybe not?
Yeah, of course, the double bond will have an impact. It's going to form the allylic radicals, which is going to make it very stable and very less reactive. And now the question is, if we compare the methyl hexanoate, like with a double bond with one of these structures where you have a hydroxyl group and hexanoate, that's going to even be more interesting because now you're having two functional groups affecting your reactivity. We didn't do this in this study, but we had another study of prenol where we calculated the rate constant. So prenol is basically an alcohol with a double bond, right? So that was interesting because it was one of the alcohols that's identified in the co-optima as a promising blend stock. And we did the calculations for the rate constant, and we've seen that just by the addition of a double bond, the rate constants of the OH abstraction really change. Like abstractions, like addition reactions become more important, like OH addition than OH abstractions becomes important because of the double bond stabilize the pre-exponential complex. So I would advise you, to go and look at that study because the double bond really had an effect. And I would believe if we considered comparing the one with a double bond with another surrogate without the hydroxyl, of course, it's going to have an effect. Like having two functional groups together would have an effect for sure. But yeah, that's a good point.
Yeah, okay, thank you.
Thank you. I don't know if there are other questions. Otherwise, I had a curiosity myself, not being an expert in this, so sorry if it's a bit... But anyway, so I was wondering how... I mean, you referred several times to this level of theory. I suppose this affects the uncertainty associated to the rates that you get. Is there today, let's say, a method which is, let's say, shared and where everyone agrees upon about assessing the uncertainties of these rates?
Yeah, usually we say that the coupled cluster calculations, like the CCSDT, are the golden method. So if you want to benchmark, we usually benchmark to the CCSDT. There are different basic sets you can add to that, augmented, different basis sets that's developed, especially by the group of Trular, and there is a lot of tables would show you the accuracy of those different basic sets. So yeah, most of the study, if they want to use G4, CBS, QB3, and they want to benchmark, they usually compare to the CCS DT level of theory as the golden method. So yeah. And I will add also to the experimental data. So there are different studies that benchmark these level of theory to some experimental studies. Like there are 2 studies from the group of Galway, Somers, and Semi. It's really good studies showing different level of theories compared to experimental data, and shows the 95% confidence, and so you can know exactly the accuracy of your rate constants at the end.
Okay, so relative to the standards, then you can define your level of confidence, let's say.
Yeah. So yeah, and that's if you can do if you have experimental data, then that's good, perfect. If not, then you can do the CCSDT level of theory. Experimental data, of course, it's only going to be available for the small molecules, but doing these calculations, we're going for 15, 16 heavy atoms. So that's why we start benchmarking to the CCSDT level of theory.
Thank you. Thank you very much.
Thank you, Alexander.
See you soon. Bye-bye.
Have a good weekend.
Have a nice weekend.
Bye-bye.